This video is about a separation principle. In the previous two lectures, two videos, I talk about the state feedback control design for linear time invariant system, and also how we can design a state estimator or state observer for linear time invariant system, such that we can use the estimated state to replace the actual state if we don't know the actual state. So one question you might have in your mind is, what if I put them together, because I can use the estimated state in my state feedback control design? Well, if I use that way, would that affect my stability of my original linear time invariant system? And how does the estimated state will impact the original linear time invariant system? And how about the transfer function, the overall transfer function? Okay, so today we're going to talk about the separation principle, which means, well, in a certain way, the control design and the state estimated design can sort of separate it, so you don't have to worry too much about the if you put them together. Okay, so here's a recap. For the linear time invariant system given by x dot t is axt plus but and yt cxt. So here we drop dx dut for simplicity. Okay, so the closed loop state estimator, as I mentioned before, is in the previous lecture, previous video, which is given by x hat dot t is a minus a x hat t plus but plus l times yt minus c x hat t. So if you have a question about why this is the closed loop state estimator, this is in my previous video explaining why this is a form for the closed loop state estimator. So this one can also be written as, because I can move this ALC and combine this one with ax hat, because they have the common term x hat t. So I can have this term. This is also my closed loop state estimator. So if we don't know the state, so for the state feedback control, we can use the estimated state to replace the actual state, because we don't know the actual state. Okay, so in other words, we can use the use of t, which is p times rt, pr minus kxt. So here we use the estimated state to replace the actual state. Okay, in my control design. Okay, it's the same form as the standard state feedback control design if we know the state. Okay. Now this is a block diagram for the closed loop control for the linear time invariant system with the estimated state feedback control. Okay, so here's a black one, which is the original one, which is a black. This one is x dot t is ext plus but and yt is cxt. So this is black portion represent that one. Of course, the black one also has a reference, the reference signal time p. Okay, and the blue actually represents the observer. It's the observer part. The observer is, we just replace, as I mentioned. Okay, we just change a little bit because here we include the control here. So we have copy the B, we copy everything we have, but we also have a, so this portion, if you look at this portion from here, this portion is the same as a black one. Okay, we add on one more term, as I mentioned over here, because we have one extra term that I mentioned over here, which is to calculate the actual output minus c times x hat, which is y. This is y hat. We calculate the difference between y and y hat, and we use a feedback. So this is plus minus, which means y minus y hat times L. This is as actual feedback. This is called closed loop feedback. Then we can use the estimated state. We do a feedback. This is the blue, and the red one is called control based on the estimated state. Because this is the estimated state, we pull it out and give a k as my feedback control gain, k, and use a PR minus kx. Okay, the PR minus kx hat, of course, kx hat, which goes to my b. Okay, is but, right? Because I do this but. This u is PR minus kx hat t. Okay, that's why this is a closed loop. This is a block diagram for the linear time invariant system with estimated state feedback control law. Okay. So there are a couple of questions when we put them together. So we have a couple of questions like, will the eigenvalues of a minus bk be affected by the observer design? Okay, if I use the standard state feedback, you sort of just connect here. You just go from this actual state, put it over here. That's what I do. If I put a whole bunch of stuff estimated over here, would that affect my eigenvalue of A minus BK? Would that affect my stability, for example? Already designed a K. Do I need to change a different K if I use the estimate state? This is what it means. The second question, will the eigenvalue of A minus LC be affected by the control design? So my observer, by the control design, for example, my original observer, I don't have this control. What if I suppose the control inside? Do I have to change my L? That's my question. Okay. The third question, what is the transfer function of the joint estimator and controller system? Like, if I would know the actual state, I have just direct feedback. I just direct feedback over here, right over here, and just all the blue portion. So that's my original. What if I put all the observer inside? What does the transfer function look like? So that's my last question. Okay. All right. So let's look at the three questions one by one. First, let's look at the closed loop system to see, hey, do I need to change the design of my K? Okay, here. So first of all, to answer the first question, let's look at the closed loop system. So the closed loop system which includes two parts. One is I still have the original x, the state x dot t, which is ax plus b ut. So here I replace ut by pr minus kx hat t. So if I do some change, because kx hat t, I put them together over here, ax hat plus but, then I do this minus b kx hat t. So here I do a change. Let's assume we have x tilde t, which is xt minus x hat t, okay, which is the same as I did in the previous video. So this is the difference between the actual state minus the estimated state. Now, by doing this, I have x hat t will be xt minus x tilde t. So I do a change is I replace x hat t by xt minus x tilde t. Okay. Then I have just here I put the x all together. I have a minus bk times xt plus bpr plus because minus becomes plus bk times x tilde t. Okay. So here x tilde t dot is a minus lc x tilde t because that's the observer or that's estimate design from the previous lecture. Okay. So if you don't know how to do this one, is from my previous video. You can see why this x tilde dot t is a minus lc x tilde t. Okay. So this one we say because now let's look at this one because this x tilde t is only depends on x tilde 0, which is the difference between x0 and x hat 0, and ALC. So this one has nothing to do with B. Okay. Of course, we don't have to care about B. It has nothing to do with K. We don't have to worry about it. B and K, not a control design. Okay. As a matter of fact, if you look at this one, the solution of for the x tilde t, this one the equation is just giving my x tilde t is e minus ALC t x tilde 0. So you sort of can see if I substitute it, because I can substitute this one by the solution over here, right? So the solution here, so I can say x dot t is a minus bk times xt plus bpr. Now here bk is the same. I just replace this one by the solution over here. So which you can see this whole portion is not relevant with respect to the k. It has nothing to do with k. Okay, so it doesn't matter what k you select. This one is always the same, right? It doesn't matter. Which means here this. So we can say this one it doesn't matter because as long as this is stable, which means eigenvalues of A minus B will not be affected by the observer estimator design. Should say use estimator design, so it's just not confusing. So it doesn't matter because it doesn't matter what estimate you design. It's okay. Your closed loop, your system is eigenvalues. The eigenvalue A minus BK will determine stability. So you can still use the original K, which also means the same way. The way to design K will not be affected by the estimator design. You don't have to care about that. You can design your controller as the way you did it, assuming that you know the actual state. Okay, that's what it means. Now let's take a look at the second question is, how about observer design? Do I care the observer design? Okay. Now if you look at the observer design, you can see x tilde t is just the A minus LC times x tilde t. Apparently, it doesn't matter what you design your control parameter, which means your control does not affect your observer design. So which means here K does not affect the A minus LC. You can still design your observer the estimator gain as you always do, right? There's no relationship between L and K. So the eigenvalues of A and C will not be affected by observer design, estimator design. Just make it a consistent estimator, which also means the way to design L will not be affected by the control design. So you don't have to worry about assuming you don't have any control, you just use the observer design you always use. That's fine. Okay. So actually the nice part of this one is come to the conclusion called the separation principle, which means the feedback control gain K and the state estimator gain L can be designed separately without affecting each other. So this kind of property is called separation principle. So this is very nice because you can have your design. So this one means that you can estimate your state. You apply this one in your PR design Kx hat t as a way, and assuming that there's no relationship, as if you are still using ut is PR minus Kxt. You don't have to worry about the observer design, observer inside, as if you're doing that. Okay, so this is nice part means for the linear, this is only for linear time invariant system. For linear time invariant system, you can separate your estimated design, the closed loop estimated, and your control design. So that's the nice part called separation principle. Okay. The last part question we want to answer is how about transfer function? If I use observer design, so I do have the original x dot t is axt plus but and yt is cxt. That's my original system, right? So your transfer function, assuming that is a ys over u sub s, it just let's do a different. So of course I have my ut given the standard state feedback is kr minus kxt. If I do replace this one, put it inside, so I have x dot t is a minus bk. Just simplify, I can do that. Time xt plus bpr t. That's one. That's what we have. So the whole transfer function, the transfer function is a y. You use a ys over r sub s. If you compute that, is csi minus. Okay, let's do this one. Okay, so ys over r sub s will be that this is the transfer function. It's given by, this is for the case when we know the state. Is just csi minus a minus bk inverse time bp. That's my transfer function. Okay, that's my transfer function for the, this is a transfer function for standard state feedback control system. So that's my transfer function. Now let's take a look at what if I use the estimated state. Does that affect my transfer function? Okay, if yes, what is the new transfer function? Okay, so to understand that, we just write it. So this is the original. We copied x dot t is a minus bk xt plus bk executed t plus bpr. So this is, let me see, this is actually from here. Okay, this is where this from. Where do we have this? So this one is coming from, okay, let's do over here. So I hope I can have, this is coming from x dot t is axt plus but. So and replace ut by is pr minus kx hat t, right? Now I further replace x has to be by xt minus x to the t. So if you this one, you give this, you will get this. Okay, if you just replace this is just replace this one by my estimated state, and also I replace the x hat by xt minus x tilde. So this is the x tilde is xt minus x hat t. So if you do that one, you get the first equation. This is about the how the actual state will change over time. Okay. The second equation is how the estimated state will, the dynamics of the estimated state, which is x tilde t is a minus lc x tilde t. So this is relation, this derivative is given in the previous video on state estimator. Okay, you can check my video on state estimator to understand why that's a relationship. So if we have these two equations, I put them together as xt x tilde t derivative. I put the stack them together. This one becomes, I put this one at a minus bk time bk, a minus bk and bk, this is 0, this is a minus lc time xt x tilde t, and plus b0 time pr. Okay, that's what we have. Okay, so if we do that way, of course I can do this one. I think I can do this one bp. Okay, right, so I can do this one. If we do whatever we have over here, okay, if we do let's see, yes, if I do all the stuff here, I can yt, of course yt is c and 0 times xt, because now I augment the state from xt to xt and x tilde t, so it's a c times 0 xt x tilde t, c0 x tilde t. So this one is my new a, I call it a bar, this is my new b, the b bar, this is my c, is new c bar. So they are sort of constructed based on my a, b, c, and also my k and l. Okay, and of course p. Okay, so because p is a constant, p is a scalar, so it doesn't matter. You can move p here or move p here. It doesn't really matter. You can put it over here. P is a scalar, so it doesn't really matter. Okay, so now for this one, I can also calculate this is ys over this transfer function, right? This is a new. This is a c. This is a new c bar time Sm minus a. This a is this whole bunch of stuff. This big augmented matrix a bar. Inverse time b bar is over here time p. So that's my transfer function. So this is come from next dot is ax plus b. This is coming from here axt plus but yt is cxt. So the transfer for this guy is y s over use of, of course here's the use of s. It's just c s I minus I use this as inverse time b. Okay. The only difference here is I have a bar, b bar, and c bar. That's it. Of course, I have a p over here. You time p, you time an additional p. That's it. Otherwise, you just follow the same formula we use for the standard linear time invariant system. So once we do that, we can do some simplification. Okay. So c is just c times 0 according to this relation, c bar. Okay, and this guy is the inverse of. So this guy is inverse of what? If I do this one, if I pull this one out, so this guy is, so Si, so this one has to be Si minus, this whole thing is A minus Bk, this is minus Bk, and this is 0, this is Si minus A minus Lc. So let's put this one a little bit further to the left. Si minus A minus Bk, this is minus Bk, this is 0, this is Si minus A minus Lc. So this is my, this will be just, this part is S minus A bar. Okay, here this I will have the same different dimension. Okay, this one will have the different dimension because if I do this one, this dimension is, let's say this is n by n. This is I n by n. This I is 2n by 2n. So that's a different. Oh no, not over here. This is 2n by 2n. So it's larger size because this is the dimension is this one, right? So if you do the inverse this guy will be, if you sort of follow this is inverse of first one time this is inverse of second one, this one. So if you use the inverse, sort of this one is still 0 and this one is something. Okay, it's determined by, of course, this is restructure, of course, right? If you do this one, but I don't really care about this value because I don't know, even I don't know this value right here, but I can compute this is 0 and this is 0, so this part will not play a role when to take the product. Okay, So the inverse this is follow the same idea about of, let's say AB0C inverse. This is sort of the inverse. This guy is 1 over AC, right? So this sort of this 1 over A0, 1 over C, this guy, some value over here, okay? That follow the same idea, okay? That's why it's the same idea over here. We do the inverse over here. This is the inverse guy. This is something I don't know. I don't care about this one from the following computation. And this guy is just inverse this guy. And we keep the B and 0 and the P over here. So if you do the product of this first two, you get C times this guy plus 0 times 0. So it's just C times this guy. The second guy is C times this guy plus 0 times C times this star, whatever it is, time B0, and of course time P. And if you do this guy times this guy plus this guy times this is 0, so we'll cancel it. It's just C SI minus A minus BK inverse times BP. Okay? So if you look at this one, this is the same as my standard state figure already derived from here. Okay? So here I rewrite again. So for the standard state feedback control system, which given by x dot t is axt plus b pr minus kxt. This is the UT, the standard state feedback control law. If we know the state, we can write this as a minus bk xt plus bpr, and yt is cxt. If we do the transfer function ys over rs is c si minus a minus bk, so this is considered a bar. If you do this, is the a bar. This is the b, for example, this is my b bar. This is c bar. C bar is the same. So the c bar is the same. Si minus a bar is my a minus bk. Inverse time bp is b, so b bar is bp. So if we compare this, the transfer function doesn't change. The transfer function doesn't change. If you even use the opposite, the estimated state, the transfer function doesn't change. So the conclusion we can have is the transfer function with the state estimator introduced is the same as original state estimator, original state feedback system without using a state estimator. This nice thing for this part is the stability part. Stability does not change if we use estimated state to replace the true state. So in other words, we don't have to worry about the stability. And also, according to the separation principle, we don't care about when we design the control gain and the state estimated gain. They can all be separated, and also the stability doesn't change. So that's why it's for the linear time invariant system. That's very nice. There's a lot of property you can use.